Kia ora koutou katoa, I'm Ko Robert Smith, toka ingoa. Hi everyone, I'm Rob. I'm a physical oceanographer and a senior lecturer in the Department of Marine Science at the University of Otago. I lead a research group at Otago, and one of our current interests is in ocean extreme temperature events known as marine heat waves. Now, some of the work I undertake related to marine heat waves is a contribution to a 5-year MB-supported programme that we're just wrapping up, known as the Moana project. And today I'm going to discuss some of the work we've been undertaking as part of this programme, focusing on something that we didn't necessarily expect when we set up that programme, which is a record-breaking marine heat wave that impacted the west coast of the South Island and the Fiordland Marine Area in early 2022. So, a little bit of background, marine heat waves, they're analogous to their terrestrial counterparts that some of you will be familiar with from those long, hot, sticky nights. These are prolonged periods of anomalously, we should say really extremely warm ocean temperatures. These events can have profound impacts on marine ecosystems. The elevated temperatures associated with these events, what can they do? They can disrupt ecological processes. They can lead to shifts in species distribution. They can alter reproductive patterns. They can lead to increased susceptibility to disease. Fisheries can also be severely impacted, as we'll hear from the speaker after me. And the economic ramifications of marine heat waves can be substantial, with industries who are reliant on marine resources experiencing declines in productivity. For these and many other reasons, understanding the mechanisms that generate marine heat waves is fundamental for us being able to better predict them or forecast these events, and also try and mitigate the impacts that these events can have on coastal ecosystems and livelihoods. Now, a little bit of background to help make the next few slides to make a bit of sense, a bit of oceanography of the region. We experience on the west coast of the South Island predominant west or southwesterly winds. What that does is it creates the thing on the right-hand side here, which is wind-driven upwelling against the coast. So we typically see, as seen in the satellite temperature image on the left, cooler waters against the coastline. There is a broad eastward flow of ocean currents across the Tasman Sea, and upon reaching the west coast of the South Island, that splits into a northward flowing cooler current, the Westland Current, and a poleward flowing Fiordland Current. As I think many of us appreciate in the room here today, this is obviously a region with really high diversity of coastal and marine habitats, and there are both substantial a substantial ecosystem value here, and this area is economically significant, especially when we come to think about some of the fisheries. Now, something quite remarkable happened in February-March 2022, is that throughout late summer and actually stretching through autumn of that year, the west coast of the South Island experienced a record-breaking marine heat wave. What's shown on the left is what this event looked like from the sea surface. The colours get a little bit blown out here with the lights, but the thing to draw your attention to is the shading here reflects sea surface temperature anomalies. These are deviations from normal. This whole area of the west coast of the South Island, it's more than 1,000 kilometres, water temperatures there were reaching 3 to 5 degrees, not 35 degrees as I got quoted in the press about, 3 to 5 degrees. I got some emails after that. But these are really, really substantial numbers. We have a reliable record of sea surface temperature globally that goes back 40 years to the early 1980s. If we look at all of the marine heat waves that have taken place on the west coast of the South Island over that 40-something year period, this particular event in 2022 stands out as the strongest, longest, and most impactful event on this coast. That's the surface view. Now, we know from work elsewhere in the world that marine heat waves do not just necessarily exist at the surface, they can extend well below the surface and impact marine life and ecosystem services to great depth. What I'm showing here is some ocean temperature profiles on the left-hand side, taken from in blue before the marine heat wave through to dark green at the peak of this marine heat wave, that were collected in partnership with commercial fishing operators working in the small section of the west coast of the South Island, who have their vessels equipped with these autonomous temperature depth sensors that are illustrated on the left, that we developed as part of the Moana project. We were lucky that we had this data available, and what it tells us is that the onset of this marine heat wave that we see at the sea surface, it was associated with a plunging of warm water from the surface down to substantial depth in the water column. If we put these temperatures in the context of what is normal on that coast, we see temperature anomalies, yes, like a few degrees Celsius above normal at the surface, but we in fact see water temperatures reaching 5 degrees above normal at almost 100 meters depth. So marine heat waves are not limited to the sea surface. They can have quite substantial vertical depth extent. What we've tried to get at in this particular piece of work is to understand what factors drove the formation and also the evolution of this one case study marine heat wave off the west coast in what is normally a really quite substantial, or can be a substantial wind-driven upwelling system. So using this nice schematic, we can start to think a little bit about what causes marine heat waves. There's a whole range of different factors. One of them is that at a local scale, warming through the ocean surface from the atmosphere can drive marine heat waves. So we can have heat waves generated through air-sea heat exchange. There's another set of processes which are important, which we refer to as advection. So it's a transport of water either laterally or vertically in the ocean. One example is heat waves can be generated through enhanced transport of warm water by horizontal ocean currents. We just call that horizontal advection. When we come near coastlines in particular, changes in vertical ocean currents, things like upwelling, changes in rates of upwelling can also modify fluxes of heat to the sea surface and lead to warming. Now, the likelihood of marine heat waves is also modified by large-scale weather and climate patterns. So we're thinking here things like El Nino, La Nina, ENSO, Southern Oscillation, and other climate drivers. Understanding what drove this particular event is fundamental for us being in a position to better predict and forewarn people about future events. We validate models with observations to make sure we're doing something sensible. The particular model we used here is something called OFAM, Ocean Forecasting Australis model. It's 3D. It's like a weather forecast, but for the ocean, and you can run this back in time to understand what might have happened in the recent past. It provides us daily fields of some key properties we can use to understand this event. I'll make it look like I know what I'm talking about. There's a word equation that does link to this little picture, but what we do is we take output from our ocean model and we build something that's really neat. It's known as a temperature budget. It's like a financial budget, but rather than income and expenditure, this budget tracks heat exchanges within a defined volume of the ocean, in our case, the west coast of the South Island, and it helps us understand the relative contribution that these different processes that I described make to the evolution of temperature over a particular period of time. So what we've done here is we've examined the contribution these processes make to this period when this heat wave first set up on the coast. Now what we found, which is different to marine heat waves in the open ocean, so when we're well away from the coast, in the open ocean, one of the key drivers of marine heat waves is enhanced air-sea heat flux. When we look at this temperature budget, and the red shading here is a greater than normal contribution, blue would be a lesser contribution, what we find is that the evolution of this particular event is not well linked to local changes in NSC heat flux. It's much more closely linked to advection. In particular, the Fiordland current that typically flows poleward along the coast, that intensified, and the Westland current even flipped direction to move down the coast. So we saw enhanced movement of warm water down the coast. We also saw, and this is illustrated on the right-hand side, a substantial amount of downwelling, which warmed the top 100 metres of the ocean by just removing the cold water that would normally be sat in that area. Now we can take a bigger view and ask a question around, well, what led to such anomalous, such unusual advection, both horizontally and vertically on the coast? Very briefly, we can look to large-scale weather analyses. One thing those highlight is that there was a period of unusually strong and persistent northeasterly winds during February and March 2022 that resulted from this big blocking high-pressure system building southeast of New Zealand. What that caused, or what it facilitated, is an onshore transport of warm water from the Tasman Sea. That can drive downwelling at the coast, and that also, through some interesting ocean dynamics, favours a warm flow to develop along the coastline. So essentially we saw a switch from a typical upwelling system to one that was strongly downwelling and drove this significant warming of depth. Now these findings have two big implications. One of them is that because this particular marine heat wave developed during a blocking high pressure system, that kind of says to us we really need to think about what generates those blocking highs if we're to better forecast these events in the future. I've got a PhD student who's just wrapping up at the moment, and Felix's work illustrates that the development of blocking highs is a common cause of marine heat waves around the country, and we can link the development of those blocking highs to some of our major climate drivers, so the El Nino Southern Oscillation, some other climate drivers, Southern Annual Node, and the Pacific Decadal Oscillation. Key thing there is that those factors help us better forecast these events. But one other implication of this work is that it illustrates that subsurface temperature observations are crucial for understanding the nature of these extreme temperature events in our coastal waters. They can help us understand the likely causes of these events, and they're also essential for validating numerical models. But we really lack in New Zealand, and Fiordland is perhaps the most lacking area of subsurface temperature observations. Because we lack sustained observations back in time, it's hard to say just quite how previous marine heat waves may have impacted through depth in this region. And as we go into the future, if we're lacking these sorts of observations in the next 3 to 5 years, when we see another one of these events and change is coming, it's very likely we will see, with continued anthropogenic climate change, more frequent and more intense marine heat waves. If we lack those sustained observations below 20 or 30 metres, when change comes, it's going to be hard to understand that change and attribute it. So the Fiordland Marine Area is relatively poor with open access ocean data, and we really need to fill that data void if we're to set ourselves up well for the future. I'll leave these conclusions up on the slides. I'll leave it there.